So today we are going to look at the performance of silicone structural glazing or bonding under extreme conditions related to typhoons. Now I'm saying typhoons, but I'm really talking about storms, rotating storms that are happening over tropical waters. So it's really just a matter of wording, and we have the same phenomenon happening in the Asia-Pacific, then it's called a typhoon. If it's happening over the Atlantic Ocean, it's a hurricane, and then around India, it's like called a cyclone. And it's all known, it's no fake news, that there is global warming, and the global warming is actually having an effect on these typhoons. So recent studies have confirmed that global warming and the rise of the temperature of the surface leads to an increase in frequency of typhoons and in strength of typhoons. So we are observing more and more intense typhoons, and on this little video you can see actually a building in Hong Kong that's being hit by the typhoon Mangkhut last year in September. So a bit more information about Mangkhut. It was the 5th tropical cyclone that hit Hong Kong in 2018, and the Hong Kong Observatory mentioned that the intensity of the storm was really extreme. So it required the highest level of typhoon signal, number 10, for 10 hours. And that was really the highest recorded since the observatory was created at the end of the Second World War. Peak intensity, we have really maximum wind of 250 kilometers per hour at the center. And that was the largest one since 1998. That results, of course, in many injuries, damage. Flying debris will smash windows. And the total damage was accounted for as 3.74 billion. So now if we have a closer look at this building that I just showed you in the video, so it's actually two harbor fronts. It's in the area of Hung Ham, and it was a project from 1993. It was originally a two-sided structural glazed wall that was using 983, which is a conventional two-part silicone that we use for structural glazing. It was refurbished partially in 2008, and when Mangkhut hit, it had then more than 10 years at least in terms of exposure to extreme conditions. Now, we had the opportunity to perform a deglazing test on these windows because, as you can see, they were all smashed. And we investigated the quality of the silicone that had been exposed to these conditions. So a deglazing test will look at different aspects like, is there indeed cohesive failure? What's the strength we obtain? Do we observe any other kind of defects like hardness change and so on? So that was all good. And it was confirmed that the silicone is actually performing well, even after this event. And this is even more visible. If you look at this enlarged picture, you see that the glass is still retained around its perimeter by the silicone, and the damage was really caused by unlocked opening windows, debris impact, which explains why there's also in other areas a requirement to do some impact testing for this kind of event. And sometimes as well, maybe the glass thickness was not properly dimensioned. On the top right image here, you see an old project, I think it was in Taiwan, and that was a gasket glazed wall. And you see the difference is that the whole window in that case was blown out, so there's no retention anymore of the glass thanks to the silicone. And so if we compare silicone structurally glazed facades with a dry stick system that is field directed, we can see clearly a big benefit that the SSG is going to happen most of the time in factory. So we have a daily quality control that can happen on the contrary of a field directed system where we will have maybe once, twice a visit of a quality auditor or inspector. Another interesting case study is Exchange Square from Hong Kong. It was built in 1984. It's one of the first SG system projects in China. It's again a two-sided SG, used 795 as structural silicone, and the dimensioning took into account 5,100 Pascal as wind load. The bite in Hong Kong is apparently always, if there's a requirement for 30 millimeter, there will be some extra added to add safety. And since its construction in 1984, actually I went on that website from the Hong Kong Observatory of Tropical Cyclones, and they were hit by, this building was hit by more than 100 tropical cyclones. So we really have here a fantastic example of durability, 35 years, still standing tall, even with all these extreme conditions. But as I said, it's like over-dimensioned. We have really a lot of silicone. And recently, we were faced with different situations. So this is Ping An International Finance Center. It's a building in Shenzhen, so it's a little bit north of Hong Kong. And it dates from 2017. So this project is a four-sided SSG, and it uses the 993N. So that's our Chinese-produced version of the two-component structural glazing system. So we have a design strength that is like our materials here in Europe, so 0.14 megapascal and 0.011. And we had to dimension for 5.72 kPa. Now, this required a joint dimension of 32 by 11, but due to frame limitation, it was not possible to accommodate this thickness. And the customer wanted to use a different joint, 35 by 8, which has also a different aspect ratio that potentially leads to different capacity to move. So we decided to perform some finite element analysis to verify that these joints that are not the conventional ones that have been already proven as working, we have those durability examples in the past, that it would still function. Now we verified loadings that were submitted by the building company of 5.72, but to take into account the fact that typhoons will continue to increase in strength over the next years, decades, we also tested for an extra wind load of 20% extra. So we also evaluated the performance of the system at 6.86 kPa. So to perform the finite element analysis, we first characterized the material, so the 993N. That is done in a very systematic way for all our silicones that are used on the facade. We collaborate with Axel Test Laboratory in the US to obtain really the pure material information, the uniaxial test piece, the equibiaxial loading, the compression information. And then out of these three master curves, we will build then, evaluate which one is the best material model. In this case, we selected polynomial second order law, and you can see here the parameters for the 993N. The software that we use is Abacus, and we use the element types that are indicated here. And in order to investigate potential failure, we decided to go into the strain or stretch space. Now, the reason for that is really that there is a direct link between what happens inside the sealant and what you measure, right? The silicone is a mix of polymer chains, and as it's being deformed, those chains will elongate, and as they reach their maximum elongation capacity, it will break, and we will observe failure. So there's really a direct link with what is happening, what is measurable. And there's also another advantage is that working with principal strains, we are independent of the material model selection. So choosing to work with a second order polynomial, or if you want to do a different fit, you prefer to work with a Neo-Hookean or a Mooney-Rivlin, you will observe failure at the same kind of strains. Now, as the industry is more used to stresses and talking in the stress space, we also add that in this case just as an illustration. But take into account that the stress results can depend on the choice of your material model, and that we don't have a real direct link at this stage between what we measure in terms of local stress and potential failure. So the first step is to perform a conversion of those macroscopic design stress values, the 0.14 megapascal that we are all familiar with, into finite element contexts. So we perform what we call a calibration exercise, and we take the joint dimension that we will use in a facade project, in this case 35 by 8, and we mesh it with the mesh that we will use as well in the facade. So it's quite important that you're not using a finer mesh inside a small element and then a coarser mesh inside a big, on the total project out of convenience, because your results will not be comparable. So when you do that, you apply a force that is a function of your bonding surface of 35, and you go towards the force that corresponds with 0.14 megapascal. You then can see how much your first principal strain is, and you can also look at the theoretical failure, 0.84 megapascal, how much do I reach? So the idea is that on my full facade, if I stay below those results, I am on the safe mode. In a similar way, if I'm looking at von Mises stress, we look at the reaction force of 0.14 megapascal, how much do I have in local stress, in local von Mises stress, and as long as I stay below that, I have safety, some kind of safety. As I said before, it's less clearly linked with the material failure at this stage. So we see that both parameters are able to nicely show the distribution of the strain stresses inside the joint. So here what you see is only the joint. So there's no substrate here, it's only the silicone layer, and you see that it's highly concentrated around the perimeters. For the facade analysis, we took a quarter of the IG unit, so that's 375 by 425, and we applied a uniform pressure that is equivalent to once and 1.2 times, so 20 times more, the design wind load. We always work with perfectly rigid frame assumptions when we do modeling. There's some discussion to have there. We are conscious that this is not reality and that frames do deflect and release some of the stress or strain that is put on the silicone. But this is our approach, so it's a more conservative approach, a more severe one than in reality. We do use the same mesh as in the calibration exercise, so 1 cubic millimeter in this case. We perform then the analysis, and we look again to the first principal strain results, and we compare those results versus what we had in the previous slide on the little H piece, where we really understand very well failure mechanism because we've tested so many of them. And as we stay below those values, we know that we are on a safe mode. Same here in the von Mises stress, we are well below what is tolerable in this case. So this concludes the review of the use of silicone structural glazing for extreme conditions like typhoons. So there's no case that has been reported where SSG has failed during such extreme wind load. It's all a matter of a quality control, of a good pre-work together with the facade designer and the silicone supplier, and make sure that we have a lot of attention to design, to testing, quality control follow-up during production, and we'll get to successful results like this. So here you're seeing Ping An International Finance Center actually showing a warning to the inhabitants of Shenzhen for the arrival of Manqut. And yeah, we're pretty sure it will be able to continue to do so for many more years. Thank you for your attention.